third edition of the hour-long Brick Breaker. And so when we last left off, we were working on the physics that we applied to our ball. And we were wondering, how are we going to rotate the ball based on where it hits an object? Now, I have an idea for that, which is, well, let me draw it out to start the episode, and then after I'm done detailing this idea, kind of getting back to a baseline, we will get started on this episode. So we already know that we need to rotate the z-axis, with this being 0, this being 180, this being 90, and this being 270. And we want to keep our ball in a range from 45 to 315 and 115 to 225. So we want to keep it within these 6 bottom and top values. Now, as far as I know, there is nothing in Unity that will tell us what point of a collider our ball hits. So if we hit here, I don't think there's, a thing in Unity that will tell us that our ball hit like 5 meters away from the center. And what we can do is we can see where the center of our cube is, and we can see where the center of our ball is. But we won't know the full length of our cube. So what I'm wanting to do is, instead of getting the cube, what if we get the cube's collider? And then we see the x position of the ball, the x position of our game object, and the maximum length of our collider. And then we can see how far, so here let's say we have x cube and x ball. So let's do x ball minus x cube, and then we want to do something with the collider width divided by 2. And with that, we can get a value which will need to be between 90 degrees. Perhaps we can also get the y of the collider and the y of the ball. Of course, with the y and the x of the ball, we're going to have to subtract it by the radius. Okay. So we have the x. So with that in mind, we have our cube. have the ball, and we have the x, y of the center of the cube, and we have the x, y of the center of the ball. So this is C and this is B. We want to determine where the ball is between, so this is the C middle, and we also want the x and the y, okay, of the C edge. Then perhaps we say something like, is B dot x less than CM dot x? And if it is, we know it's on the left side. Otherwise, we know it's on the right side. Okay? And then what? So we need to convert this distance to 45, where 0 is equal to 45, and whatever the max is, or the edge. What? Oh, sorry. 0 will be equal to 0, and the max edge is going to be equal to 45. Okay. So then if we do CE minus CM dot x, we are given the length of this. Then we do the length minus the b of x, and we get the, no, then we do the cm minus the b of x. No, this would also be b of x divided by c of m, or sorry, subtracted by c of m. So then we have the b dot x minus c dot m, and we get the x position and then, well, let's try to write this out. Okay, so what if this was at world center, this was at 5, and this was at 3? So that would be, okay, let's make it a bit easier for us. This is 10, this is 5, and this is 0. So we would want 50% of 45. Okay, so then we want length divided by x position, right? 10 divided by 5, that'd be 2, yeah. 5 divided by 10 would be 0.5. Okay, so then no, we actually want the x position divided by the length. The x pose over the length, or in this case, it would be 5 over 10, which would equal 1/2. And whatever this equals, say it equals A, we need to multiply that with 45. So then A times 45. Actually, this would be negative 45. So A times negative 45. And so in this case, it would be 45 times 0.5, which would be 22.5. So in this case, we would have, let's just show a new layer for this. So in this case, 0, 10, 5. And we want it to, since it hit this side, it's going to go up, and because it's here, it's going to go, this direction, 45. So this is negative 1 in the 45. So it's going to go off like that. If it, no, sorry. Let's fix that. That's not 45, it's 22.5. So that's about 45, that's about 90. So it's going about here. So this is the degree here is negative 22.5 as the ball goes up. So, two things is to determine what side of the cube, so side of cube or collider, and then we want to use the math formula that we just came up with of x position divided by the length multiplied by 45. Okay, well, let's start our timer now and see how far we can get. And see if this math is even viable. Okay, so let's do this from our ball controller. Let's wait for these to load. Let me actually move my Photoshop to my other screen so I can see that at the same time. Okay, so now we are at the on-collision intake. One of the things that I was thinking of is we would get the collider size. Yep. So let's do this. We'll keep our debug break. We want to say ball position equals, and then let's say collision position equals, but then let's also try to get the collision collider. So let's say box collider equals collision.get component. Okay, collision.gameObject.get component of the box collider type. Then we want to print the box collider, and let's try getting the size and center dot center size. Okay, and let's see what this gives us. Okay, 16 minutes into the stream, not 16 minutes into the timer. So we've got a brick in the scene, we've got the ball. Let's just manually move up the ball. Okay, perfect. So now our ball position is 0, 1.5, 0. The collision position is 0, 2, 0. We see that the ball is less than the collision, which means that the ball would go down. We see that the center is 0 and the size is 1. I'll have to redo the math to include the center in the size calculations. I think I would just do center plus size. You know what? I'll still keep it in there just for the sake of that. And yeah, I see that the zero and 0 with a max distance of 1. Right. Oh, we also need the scale. Okay. Yeah. Right. Okay, so we need to include the scale of the brick as well. So let's say print collision.transform.local scale. Okay, let's print this out, and then we will start to create a more mathematical equation that we can copy. Okay, so move the ball up. There we go. Yeah, let me use Photoshop. So I'll put this, there we go. I'll put this over here. Let me drag this over here, my tablet. So, What we want is we want the okay, so let's say x equals size minus center, yeah, or center plus size. No, it would be center plus position. Yeah. So we'll say the x equals the size. Perhaps it can be size, yeah, size plus center. Y equals position plus center. And looking at our previous formula, x is now going to be the edge. Yeah. So let's label that as the edge, and this is the middle. And what we want is we want the edge minus the middle. So x minus y. Which is pretty much saying size plus center minus position plus center, and we have center minus center, so we can cross that out. So center doesn't actually matter here, so we have the size minus the position. Okay? Yes. So size minus position, and then we have the what is that? The edge? No, the middle. Okay. And then we have the ball minus the middle. And so let's say z equals ball minus middle. I don't know, let's say a equals size minus position. Okay, we have the ball minus the middle. Then we want to do z divided by b. Oh, sorry. Z divided by a. Or, this is also so ball minus the position plus the center divided by the size minus the position. Okay, so ball minus position plus center divided by the size minus the position. And we want to multiply that by 45. So times 45. And that should give us the degree of rotation that we want. Okay, so let's go into our script and make this a reality. So let me say vector 3 ball equals the transform dot position. We'll say the vector 3 position equals collision dot transform dot position. Let's say let's take this below so we can use our box collider. Okay, so we have the position, we have the ball, we want the center, we want the size. So let's say vector 3 center equals our box collider dot center, and the vector 3 size equals the size. We also want the scale. Yes, how are we using the scale with this? We forgot to talk about that. So the scale would affect the size. It would not affect the position, but it would affect the size. Yeah. So then we need to do size times scale. So scale times size minus position. Then we should also get the ball times scale. Okay. Then let's also get the box collider of the ball. So serialized field box collider BC. Then our ball is going to be the transform dot position times scale? No. Plus scale? No. Times 1 point scale? Whew, this is tough. What about the position plus the scale? No, not on the ball, because we want the very center of the ball. So then perhaps we can remove that. Okay. Then what if we get just on the edge. The size and the box collider size is 1, 1, 1. So yeah, we want the size times scale times the collision.transform.local scale. You can't multiply? Huh, I feel like there should be some shortcut to do this. So let's say unity multiply vector 3. Okay. So let's try that. I feel like that should be a... Okay, vector 3 multiply. So, vector 3 dot multiply. No? Come on, Google. Perhaps this is a mathf type thing? Are we sure this is C#? It says C#. Perhaps it's a system vector 3. Maybe if we type system dot... No, vector 3 is the Unity engine vector 3, not the C# vector 3. System.numerics. Well, what about mathf? Mathf dot oh well. System dot numerics dot vector 3 dot multiply, and does that work? Convert from Unity engine vector 3 to system numerics vector 3. Unity convert Unity engine vector 3 to... You know what? Let's just make our own multiply function. That's easy enough. So vector 3 multiply is going to take vector 3, I don't know, what do they call theirs? Left and vector 3. Right, I like that. Okay, and what this is going to do is it's going to return a new vector 3 of left dot x times right dot x left dot y times right dot y left dot z times right dot z. Okay. And then let's just destroy all of that, and there we go. Okay. So our size is our size times our local scale. Okay, we have the ball, the position, the center, and the size. Let's do this of float angle of rotate. And we will set that to 45. Now to get the float degree of rotation is going to be equal to everything times the angle of rotate. So the first thing is going to be and then divided by, so the left side is the ball dot x minus the, so ball minus position plus center dot x divided by the size minus position dot x. And then let's print degree of rotation equals plus. And what does this give us? So we expect it to give us about 22.5. Okay, we have the ball moving up. 0. That is very possible if, okay. Well then let's print it out along the way. So let's say float top equals float bottom equals top bottom and then we print top and print bottom okay, and if we play this out, let's see what we get. Okay, move the ball up. Top is 0. The bottom is 2. Now why would the top be 0? Ball minus position. Well, duh. Of course it's 0. We want it to be 0. It's not 22.5, it's 22.5 if it's halfway over. Gosh. Okay. So let's see. What if we move the x to 0.5? Now it should be 22.5. 11.25. Interesting. Top is 0.5, yes. The bottom is 2, though. Why is the bottom 2? So the size minus the position. And the size is the size times the scale. We want it to be 1. Oh, size times scale divided by 2. Let's try that. Okay, we'll play it. We'll move this to 0.5 and we'll slide it up. There we go, 22.5. Okay, move it down, turn it off. What if we put the position all the way to 1? We move it up. Okay, 45. Now, -1, -45. So, do I want to flip the values then? Because I do want it to be positive on the other side and negative on this side, right? Well, let's do this. Let's have a serialized field bool test equals false. Then we say if test else RB dot velocity equals 0. Equals vector 3 dot 0. Okay. Then let's remove this debug break, and we want to rotate the z. So we say transform dot rotate new vector 3 0 0 degree of rotation. Okay. Waiting for it to move. I haven't pressed play yet. Okay, wrong way. 0. Okay. we need to apply the y. So let's apply the y first. And what is this? Why am I printing the velocity? Because I just copied the whole thing lazily. Okay. So now we just want to see, is the ball below above or below collision? So this would be transform.position.y minus the collision.transform.position.y, and let me just print this. And let's say y plus okay, let's get a few values for ourselves. Play it. Move the y up. Y is negative 0.51. Okay, set it at 3 and move it down. Y is 0.52. Yes, so if y is positive, so we want to say float direction equals instead of typing it out again, let's just copy everything here. The float direction is equal to the transform position y minus the collision transform position y. And then we say greater than 0 question mark 0 else 180. And the x will take the direction. Okay. So now it should also flip its direction as well. Let's play it. Set the direction to up. Click test and perfect. And a Z to, nope. But let's move the X over 1. And test. So we need to flip it. Yeah, I was thinking that we would need to, but okay, now we definitely know. Let's just try a negative degree of rotation. I'll try putting the ball above it afterwards. We'll see what happens. So the X of 1 for the ball. Let's play it. Rotation of up. Go to test. Perfect. 0. 1, 3. Now it should go and smack on this, and we want it to go to the right. Okay. Then, what is our degree of rotation? 45. Okay, let's say, transform dot rotation equals quaternion dot identity. So we reset it to 0 before we rotate. What does that do to us? Play it. 0. Check our time. 20 minutes left. I think we can get it done. Perfect. 0, 1, 3. Okay. Zero, 1, -4. So interesting. 0, 0, 0, 0. -1. Good. Well, that's fun. It shows it like moving. Okay, it's going down. That's what we want. 0, 1, 4. And test. Okay, it seems to be good. What if I turn my paddle back on? Let's put the ball at 2.2 with test on, and let's see what happens. Okay, that was interesting. So we saw it go the wrong direction when it hit the paddle. Huh. Well, what if I have it at 180, I have it at 3, and I have it at -0.5, and I press play. Okay. Then what happened with the paddle? Is it because it touched the paddle many times? Let's turn on all of our other bricks. something interesting is happening when it touches our paddle. Let's keep trying to find out what that is. It's not moving at nearly the degree it should be. Oh yeah, it just touched it and went in the opposite direction. What if we say bool above or below equals above or below, and then let's say that our degree of rotation multiplied equal to above or below negative, 1 else negative 1. So now it's going to change based on, is it hitting above or below? No. The rotation just seems to be very small. I think it's safe to remove that. No, let's just undo. Yeah. And then when we get here, I will say if collision dot transform dot tag dot equals our tag holder dot paddle dot toString. Oh, then let's do a debug dot break. degree of rotation of negative 10. Okay. A degree of rotation of 6. Huh. Is it really going off of 45? So it's the top divided by the bottom times the angle of rotation. So what is this? 0.75 divided by 5.34. Okay. Huh. And the top and the bottom is the ball position, the center. Would it work properly with the paddle if I flip the top and the bottom for the paddle? Let's try it. Okay, so it definitely doesn't work for the bricks, but let's see if it works for the paddle. A degree of rotation of negative 67. No. So that's definitely not the solution. Should have known. Then why are we getting such crazy values? You know what? Could it be that this is turning on? Let's remove that on trigger enter as well, just in case. No way. Then it must be that divided by 2 for the scale and size is backfiring on me. Size 111, scale 255. No? The same scale and size. So that can't possibly be it. Could it be rotation. So what if I took all of my bricks and put them at -1, but I took my paddle and I put it at 5. A degree of rotation of 3 now. How can the degree of rotation for my paddle be so small? So the ball minus the position plus the center. This is all from our collision object. Okay, this might just happen to be... I would love to solve this. Okay, let's take the calculations of a brick hit and the calculations of a paddle hit. And let's write them all down and see what the difference is. Okay, there's our paddle hit, and there's a brick hit. Okay. Not allowed to resize my Photoshop right now. Annoying. Okay. So, paddle. We have the ball at -0.5, -2.50. We have the paddle at -0.73, -3, and 0. We have the scale at 2.5.5. We have the center at 0, 0, 0. We have the size at 1, 1, 1. The top is 0.23. The bottom is 1.73 with a degree Okay, so kind of all of the degrees of rotation are pretty bad. I thought the degree of rotation was okay. So let's try 0, 0, 1, go. Yeah, that gave it a negative 30. Zero, 0, 1, could it be something with how I'm adding force? Okay. Then instead of this, what if I say transform dot local position plus equals a new vector 3 of 0, 0, speed times time dot delta time. Will that move it forward in a straight line? Because I think our rigid body is messing with our calculations. Okay, this is bad. Okay, our time is up. I think we need to find a new way of moving our ball. Well, we will look into that next. It looks like we've finished our rotations, but we need to continue working on how we are going to move our ball in the z-axis. So, thanks for watching. If you like it, subscribe, or like it. Yeah, thanks for watching. Have a great day.